2318 students, this is the second part of those 6 topics that we need before moving into section 5.3, which is talking about diagonalization, one of major topics that we're getting close to. There's a couple of tools you need. We already talked about the first 3 on that list there. So right now we're going to talk about number 4, which I'm calling Lemma 15. That if lambda is an eigenvalue for a matrix, then lambda is also one for the transpose of that matrix. This is another one of those short and sweet things that you should be able to prove yourself on an exam, okay? So if lambda is an eigenvalue for A, that means there's a non-zero vector such that this statement is true, right? Definition of an eigenvector, eigenvalue. And that's equivalent to stating that this homogeneous equation has a solution, as we've been using to calculate eigenvalues by finding where the determinant of that is non-zero, right? So we'll let B equal to this matrix A minus lambda I. Okay, then that equation there is the same thing as saying Bx is equal to 0. Has a non-trivial solution, just because we said up here that this has a non-trivial solution, right? An eigenvector. So this has a non-trivial solution that implies B is not invertible, right? Why would that be true? Let's see. Oh yeah. By the invertible matrix theorem, right? That thing that we've been proving more and more parts of during the course. All right, if B of x has a non-trivial solution, that means its kernel has non-zero vectors in it, so its dimension is greater than 0, et cetera, et cetera. So therefore B is not invertible. All right, so now I want you to recall lemma 4. That said if A is invertible, then its transpose is invertible. Another one of those really cute little statements with a short, sweet proof that is a good exam question. Make sure you can prove that, right? That is a statement P implies Q, right? Now, whenever a implication is true, whenever P implies Q is a true implication, its contrapositive, which is equivalent to it logically, is also true. Contrapositive P implies Q is not Q implies not P. So the contrapositive of lemma 4 is that AT, the transpose of A non-invertible, implies that A is non-invertible, right? Well, let's just apply this to this matrix B, right, which is the transpose of B transpose. Remember that. So B non-invertible implies B transpose is non-invertible by the same logic. So that means B transpose X equal to 0 has a non-trivial solution. And, well, B transpose, what was B? B was equal to A minus lambda I. So B transpose is A minus lambda I, the quantities transpose. Remember the properties of transposes? I think it's chapter 2. Says that if you have a linear combination of matrices, the transpose of them is the linear combination of their transposes. So this is equal to A transpose minus lambda I transpose. The identity matrix transpose is just itself. So we have the B transpose, which has a non-trivial solution, is the same thing as saying A transpose minus lambda I has a non-trivial times X equal to 0, has a non-trivial solution. Are you getting that? Let's see. Oh, there we go. So B transpose has a times X equal to 0 has a non-trivial solution, gives us A transpose minus lambda I X has a non-trivial solution. In other words, that lambda is an eigenvalue for A transpose. QED. All right. All right. Now, number 5 over there. A key observation is that if a linear transform leaves a subspace invariant or fixed, then lambda equal to 1 is an eigenvalue for the associated matrix A. And often that lambda equal to -1 will be an eigenvalue for it as well. examples of the type where the transformation, the linear transformation, is reflecting the plane R2 about the line y equal to mx, which goes through the origin, have eigenvalues like lambda equal to 1 and lambda equal to -1. So let's look at an example over here. So consider this transformation. I've got some glare going on. Let's see if I can move this. Yes, that should eliminate that glare there. Okay. So consider the transformation R about x equal to y. That reflects all vectors in R2 about the line y equal to x. So here's R2, here's the line y equal to x. I'm going to call that L1. And this is a linear transformation from section 1.9. You learned how to come up with its standard matrix. Stop the video, do that right now. Come back. What's in there? Well, the first column should be t of e sub 1. If you reflect that about y equal to x, you land right on e2, which is 0, 1. Second column should be t of e2. If you reflect that about y equal to x, you land right on e1, which is 1, 0. So there's this matrix. That is the standard matrix for that linear transformation, right? So you're back onto everything you knew from section 1.9. Now notice that the set of all vectors x, y, where x is equal to y, in other words, line 1 here, is invariant under this transformation, under this reflection, right? If you reflect across a line, you don't actually move anything on that line. So, for example, if you were looking at let's see, you're looking at the vector pi, right? That's on there. If you multiply a by pi, what do you get? Well, let's see, that first row is going to just pick up the pi and put it in the first spot. Second row is going to multiply by that, it's going to pick up, yeah. So that's just going to go right to itself, pi. Okay, so so not only is this line, this space, subspace, y equal to x, invariant under it, it satisfies this, that a of x is exactly equal to x. But that's the same thing as saying ax is equal to 1 times x for all the x's in that. So if you have an invariant subspace of fixed points, you can have other invariant subspaces. In a second, you'll see those. These are all fixed. So for each of those fixed point type vectors, lambda equal to 1 is its eigenvalue. In fact, you can prove using that matrix that the eigenspace for lambda equal to 1 is the same thing as S, is the same thing as L1. You should use that as a little review. Make sure you can do that. Okay, now, if you have a subspace that's invariant in R2 and it's one-dimensional like this, then there is always an orthogonal line, right? And what happens with that orthogonal line, let's call that L2, if you take any vector in there, let's see, what would be a vector in here? Let's say we're looking at 4, -4, right? What's going to happen if you multiply it by this matrix? Well, that first row is going to pick up the -4. That second row is going to pick up the +4. Where's that? So the image of this vector v, t of v, is sitting right over there. T of v is right up there. Well, you'll notice that AV is equal to the opposite of v. And that's not a mistake, that's not an accident. So we have here that for this vector v, it is an eigenvector for lambda equal to, stop the camera, fill in the blank, and go and prove that this is an eigenspace for that lambda. Okay.